Heat is a restless form of energy, always on the move. It never stays still, always seeking to balance itself out. This constant motion is what drives many of the processes we see around us every day. It seeks equilibrium, constantly flowing from hotter regions to cooler ones. Whether it's the warmth of the sun melting ice or the heat from a fire spreading through a room, heat is always on a quest to even out temperatures. This relentless dance of thermal energy shapes our world in countless ways, influencing everything from the weather we experience to the way our homes are heated. The transfer of heat is a fundamental aspect of our daily lives, from the weather patterns that govern our skies to the cooking methods that nourish our bodies. Heat transfer is at work. The swirling clouds of a hurricane and the bubbling of a pot of soup are both driven by the movement of heat. Among the many ways heat travels, convection stands out as a fascinating and fundamental process. It's not just about heat moving from one place to another, it's about the movement of fluids, like air and water, carrying heat with them. It's the driving force behind boiling water, soaring hot air balloons, and the very circulation of our atmosphere. When you see a pot of water boiling, you're witnessing convection in action. The same goes for a hot air balloon rising into the sky. In this exploration, we'll delve into the captivating world of convection, uncovering its secrets and appreciating its profound impact on our lives. We'll see how convection currents form and how they influence everything from weather patterns to cooking techniques. We'll journey from the basic principles that govern its behavior to the real-world examples that illustrate its power. By understanding convection, we can better appreciate the dynamic nature of our world and the forces that shape it. So, fasten your seatbelts as we embark on this enlightening adventure into the heart of heat transfer. From the smallest pot of boiling water to the vast atmospheric currents, convection is a key player in the story of heat. Convection, in its essence, is the transfer of heat through the movement of fluids. This process is fundamental in many natural and man-made systems, playing a crucial role in weather patterns, ocean currents, and even in the heating of our homes. Unlike conduction, which relies on direct contact between molecules, where heat is transferred from one molecule to another through vibration and collision, convection depends on the bulk flow of matter. This means that large groups of molecules move together, carrying heat energy with them. Imagine a pot of water simmering on a stove. The heat source at the bottom of the pot warms the water molecules in direct contact with it. These water molecules, now energized by the heat, begin to move more rapidly. As they gain energy, they become less dense and start to rise towards the surface. These heated molecules become less dense and, like tiny buoyant balloons, rise to the top. As they ascend, they carry the heat energy with them. As the hot water ascends, cooler water from the top, being denser, descends to fill the void left by the rising hot water. This cooler water is then heated by the heat source, and the cycle repeats. This continuous cycle of rising warm fluid and sinking cool fluid sets up what we call a convection current. These currents are responsible for the even distribution of heat within the fluid. This elegant dance of molecules effectively transfers heat throughout the entire volume of water, ensuring a more uniform temperature distribution. This principle of convection is not only limited to water but can be observed in air and other fluids, making it a universal mechanism for heat transfer.
Convection often occurs spontaneously in nature, driven by the inherent density differences that arise from temperature variations. This type of convection, aptly named natural convection, is all around us. Consider the gentle sea breeze that graces coastal areas on a sunny afternoon. The sun's warmth heats the land more rapidly than the water. As the air above the land warms, it becomes less dense and rises. Cooler air from over the sea, being denser, flows in to replace the rising warm air, creating a refreshing sea breeze. This is just one example of how natural convection shapes our environment.
While nature excels at driving convection through natural processes, we humans have learned to harness and enhance this phenomenon for our own purposes. Forced convection, as the name suggests, involves the use of external forces to propel the fluid and accelerate the heat transfer process. Think of a convection oven, a marvel of culinary engineering. A fan strategically placed within the oven cavity circulates the hot air, ensuring a more even and efficient cooking process. This forced circulation eliminates hot and cold spots, allowing for consistent baking results. From hair dryers to car radiators, forced convection plays a vital role in numerous technological applications.
Convection's influence extends far beyond our kitchens and household appliances. It's a fundamental force shaping our planet and beyond. In the grand theater of weather, convection takes center stage. The sun's radiant energy heats the Earth's surface unevenly, triggering massive convection currents in the atmosphere. Warm, moist air rises, cools, and condenses to form clouds, which can unleash their stored energy as rain, snow, or hail. These atmospheric convection currents drive our planet's wind patterns, weather systems, and even the fury of hurricanes.
Section 6. Measuring the heat flow. Convection's equation. To truly grasp the power of convection, we need a way to quantify the rate at which heat is transferred through this process. Convection is one of the three primary modes of heat transfer, alongside conduction and radiation. It plays a crucial role in various natural and industrial processes, from the warming of our homes to the cooling of electronic devices. Fortunately, scientists and engineers have developed a mathematical expression that captures the essence of convective heat transfer. This expression is not just a theoretical construct, it has practical applications in fields ranging from meteorology to mechanical engineering. By understanding this equation, we can predict how heat will move in different environments, which is essential for designing efficient systems. This equation, known as Newton's law of cooling, provides a powerful tool for understanding and predicting the behavior of convection in various scenarios. Newton's law of cooling is fundamental in thermodynamics and heat transfer studies. It helps us understand how quickly an object will cool down or heat up when exposed to a fluid, whether it's air, water, or any other substance. The equation states Q equals H dt, where Q represents the rate of heat transfer, H is the convective heat transfer coefficient, A is the surface area involved in the heat exchange, and dt is the temperature difference between the surface and the fluid. Each of these variables plays a significant role in determining the efficiency and rate of heat transfer. The convective heat transfer coefficient, H, depends on the nature of the fluid and the flow conditions, while the surface area, A, and the temperature difference, dt, are determined by the specific setup of the system. This seemingly simple equation allows us to calculate, for example, the rate at which a radiator warms a room or the cooling power of a computer's heatsink. By applying this equation, engineers can design more efficient heating and cooling systems, ensuring optimal performance and energy efficiency. Whether it's in the design of HVAC systems, automotive cooling systems, or even in the study of climate patterns, Newton's law of cooling is an indispensable tool in the field of heat transfer.
Section 7. Conduction versus convection. Two ways heat travels. While both conduction and convection play crucial roles in heat transfer, they operate through distinct mechanisms. Conduction relies on direct contact between molecules, with heat flowing from regions of higher temperature to regions of lower temperature. Imagine holding a metal spoon in a cup of hot coffee. The heat from the coffee transfers to the spoon through conduction, causing the spoon to warm up. Convection, on the other hand, involves the bulk movement of a fluid, carrying heat along with it. In our coffee example, convection currents would also develop in the coffee itself, distributing the heat more evenly throughout the cup.
Section 8. Convection. A force of nature and engineering. Convection, as we've discovered, is far more than just a scientific concept. It's a fundamental process woven into the very fabric of our universe. From the grand cycles of Earth's atmosphere and oceans to the intricate workings of our own bodies, convection plays an indispensable role. Its influence extends from the depths of Earth's mantle, where it drives the movement of tectonic plates, to the vast expanse of space where it governs the energy balance of stars. Engineers and scientists continue to unlock the secrets of convection, leveraging its power to design more efficient heating and cooling systems, predict weather patterns with greater accuracy, and even explore the cosmos. Section 9. Beyond the horizon. Convection's enduring impact. As we conclude our journey into the world of convection, we're left with a profound appreciation for its elegance, power, and ubiquity. Convection is more than just a mode of heat transfer. It's a fundamental force that shapes our planet, drives our weather patterns, and enables countless technological marvels. By understanding the principles of convection, we gain a deeper understanding of the natural world and unlock new possibilities for innovation and exploration. As we continue to unravel the mysteries of heat transfer, convection will undoubtedly remain a central focus, guiding us towards a future shaped by the dance of heat and the flow of fluids.